Okay. So today I'm going to go from basic feasible solutions, basic optimal solutions, and start getting into the simplex method. And when I give you a sketch of how the simplex method works, it should seem like there's no way that this could possibly be a legitimate proof strategy. It should look like we're going to argue in circles. And fortunately, there's going to be a trick that will save us. So before we can get into the simplex method, which actually shows us how we can solve certain linear programming problems, I want to just quickly review again the definition of a basic feasible solution and a basic optimal solution. So remember, what is our framework? So the setup is we have AX equals B, X greater than equal to 0, and we want to minimize X transpose C. So this is the setup. And we talked about how you can always put a linear programming problem into this canonical form and how useful it is to get something into this canonical form. And then we said a feasible solution is just an X where the entries are non-negative and satisfies this. An optimal solution is a feasible solution where this is minimized. Okay, so feasible and optimal are what we expect them to be. We showed that it's not always the case that you have a feasible, it's not always the case you have an optimal. If you have an optimal, it's not always the case you have a unique optimal. But in general, we hope that we should be able to find at least one optimal solution to our problem. And the question is, how can we find it in a reasonable amount of time? And that's where this idea of basic feasible and basic optimal is going to come into play. Is if we're looking for just any feasible solution, if we want to just prove that something can happen, all we have to do is find one. And so basic feasibles is restricting our search. And so you add the word basic with the following script. So let's let X be feasible. Let XL1, XLK be the non-zero entries of X. And then let's let AL1, ALK be the corresponding columns of A. So again, when we look at the matrix A acting on X, we can write this as here's A1, here's A2, here's A, so let's see, we're always doing it, it's, what is it, n columns. So AN acting on X, and this is just going to be A1X1 plus AN XN equals B. But of course, all that matters is the entries of X that are non-negative. Yes?
What is the what column?
I'm sorry?
ALKB. I don't get that.
Which? These?
No, the second line to the last.
This one? Right here?
The second one. Be the what columns of A?
Be the corresponding columns of A. So, some of the entries of X are going to be 0, some of the entries are not going to be 0. Whichever ones are not 0, we're going to call these the L first, the L second, the LK. So we'll say that there's K entries of X that are non-zero. And let's let these be the corresponding columns of A. So when I do this multiplication out, if one of the x's is 0, that column doesn't contribute to this. This is the same as AL1X1 plus ALK XLK equals B. Right? I don't need the columns of A that correspond to x's that are 0, because they don't contribute to this. And so we'll say you're feasible if AL1 through ALK are linearly independent. And so remember, linearly independent means that the only linear combination of these that vanish is when all the coefficients are 0. That means U1 AL1 plus dot 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 plus UK ALK equals 0 if and only if u1 equals u2 equals uk equals 0. Okay? So that's what we mean when we say we have a basic feasible solution. It's a feasible solution and the corresponding columns are linearly independent. So it's not immediately clear that if there's a feasible solution, there has to be a basic feasible solution. And of course we can do a search and replace. Instead of the word feasible, what could we write? What's the other word we'd care about? It would be, after studying feasible solutions, what do we study next? Optimal, right? So all we would do is we would just replace this, and x is optimal, yeah, blah, 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 blah. It's an optimal solution, and the corresponding columns are linearly independent. Okay, so do basic feasible solutions exist? Well, not always, right? We have examples of linear programming problems where there's no feasible solutions. So if there's no feasible solution, there can't be a basic feasible solution. But the theorem is, if there is a feasible solution, there's a basic feasible solution. And moreover, there's only finitely many of them. That's the wonder. And so, when we're trying to solve, there's no way to optimize the problem if there's no solution. If we can't even find a feasible solution, forget about optimizing. So step one is to search for feasible solutions. And rather than search for feasible solutions, this theorem tells us it's enough to look for basic feasible. So theorem. If there is a feasible solution, there is a basic feasible solution. Which is wonderful, right? It means we can concentrate on just looking for feasible solutions. What's the next thing you would expect after this?
If there's a basic feasible, there is an optimal.
No, all right? Because we know, unfortunately, that it's not always the case that there's an optimal solution. You're close. It has to involve optimal. So the next thing would be, if there's an optimal solution, then there's a basic optimal. So theorem. Above is feasible going to optimal. Right? So we're going to basically spend the rest of our lives just looking for basics. And there's one more thing which is surprising. There are only finitely many basic feasible solutions. Now that's very nice. We saw examples before where there were infinitely many feasible solutions, or where there were infinitely many optimal solutions. There are only finitely many basic feasible solutions. Now this theorem, the second theorem, tells us if there's an optimal solution, there's a basic optimal solution. So what can you immediately deduce as a corollary?
Finitely many optimal.
Good. Finitely many what?
Basic.
Basic, right? Only finitely many basic optimal solutions. Right? It seems like we're making progress, right? We've gone from an infinitude of things to check to finitely many. I was talking with a colleague recently about shuffling a deck of cards. So 52 deck of cards, and someone deals the cards. What's the probability that this particular shuffling, that this particular ordering of the deck has ever happened before? So you have a deck of 52 cards, you shuffle it. How many different ways can I order a deck of 52?
52 factorial.
52 factorial. I'll leave it as an exercise for you to calculate how large 52 factorial is. 52 factorial is clearly greater than or equal to, I think, 10 to the 42. Just to give you some sense of how big it is. Right? Because everything from 10 and up is at least 10. So this is at least 10 to the 42. Just because it's finite does not mean it's small or practical to check. Right? So if we just leave these as finitely many, we're not doing a good job. We have to somehow get that finitely many down to a manageable size. And that's where the simplex method will come in. The simplex method will talk to us and tell us how we can actually search this finite space efficiently. But it's first useful to reduce our searching space, to reduce where we're looking to this finite set. So what I'm going to do is I'll prove the first and the third, and I probably won't prove the second one, that if there's an optimal, there's a basic optimal, because the proof is almost identical to the proof of if there's a basic feasible, there's a feasible. Okay, so let's prove the first theorem. So if there's a feasible solution, there is a basic feasible solution. And because we don't have much blackboard space, I will erase this. Okay. So, well, all we know is there's a basic solution. So, let X be a basic solution with, say, XL1, XLM, non-zero entries. There's two possibilities. What are the two possibilities? So what are we trying to show? What are we trying to prove in this theorem? So given a feasible solution, what are we trying to show? No, that's the third one. Given a feasible solution, we're trying to prove there's a...
You wrote a basic solution.
Oh, I'm sorry. No wonder you haven't told. Let X be a feasible solution. Sorry. So what do, okay, sorry. So let X be a feasible solution. So what are we trying to prove?
There's a basic.
There's a basic. So a solution is basic if the corresponding columns are linearly independent. So there's two things to look at. What are the two cases we should split by? So I want you to get a sense of how you should attack these proofs, right? What should case one be? So the goal is find a feasible solution with linearly independent columns. So let's break this into cases. So what should case one be? So we have a solution. We can look at the corresponding columns, and what should case one be about the columns? Columns AL1, ALM, are what?
Are already linearly independent.
A linearly independent. Alright. Here's the challenge. The columns are linearly independent. Can you find a basic feasible solution?
Yes.
Yeah! Yay! X is basic. Right? It's always a good idea to split things into cases. When you split things into cases, you have more information at your disposal. So, if the columns are linearly independent, we have our basic feasible solution. Okay, so now that we have a basic feasible solution, case one is done. So now we go to case two. The columns are, now we just add the word not, linearly independent. Okay, so if they're not linearly independent, what does this mean? We have constants gamma 1, say gamma n, such that AL1 gamma 1 plus ALM gamma m equals 0, but not all gamma I equals 0. That's what it means to be linearly dependent, is that I have some kind of relationship like this, and it's not the case that everything vanishes. Okay? So, one of the gammas is not 0. Without loss of generality, or if you want, relabel, assume gamma 1 is not equal to 0. Does it really matter which index is not 0? No. But just for ease of, notation, let's just assume it's the first one that's non-zero, just for definiteness. So we're going to relabel the indices and we'll assume that it's gamma 1 that's not 0. Now, something else has to be non-zero as well to balance it out, but we don't need that. All we need is something is non-zero. Okay, so what we know is the following. Let's look at A, the notation is a little bit annoying, times x plus lambda gamma. Okay? So what does this mean? Well, gamma is basically going to be padding my vector gamma to put zeros in all the other corresponding places. I want gamma and x to have the same size. Right? So right now I've got a couple of x's that are non-zero, and these correspond to certain columns. These columns are linearly independent. Form a new vector that's 0, except at those columns where the values are gamma 1 through gamma n. Well, this is just going to be ax plus lambda a gamma. Well, what is a times gamma? It's just
0.
It's just 0. Because a times gamma is just this piece here. So this is just ax. But what was ax? It's just b, right? So we have a new solution. This is a new solution. Notice I didn't say it's a new feasible solution. I just said it's a new solution. Why might it not be a feasible solution? What could prevent it from being feasible? I mean, it solves the problem. What else is missing? What else must be true?
Just in case it doesn't satisfy all the constraints.
Okay, so what's the constraint that we haven't talked about?
Lambda.
So it's related to lambda.
X has to be prioritized.
The components have to be non-negative.
Yeah.
Maybe some of these components are negative. Well, let's think. This works for every value of lambda. Can you give me a value of lambda such that this will definitely have its components non-negative? What's the simplest value of lambda to take? 0. So it's feasible if lambda equals 0. So what I want you to do now is I want you to think of lambda as a knob. It's a dial. You can turn it up. Or if you want to turn it down, make it negative. You can choose which direction you're going. What we're going to do is we're going to choose lambda to cancel out one of the coefficients here. So what we're going to do is, I don't want to write this out in full detail. I've done this in the notes and I want you to think about this. Let's just do a specific example. Let's say the corresponding elements of x are 2, 4, 8, and 7, and the corresponding numbers are 11, 3, -2, and 1. Now I multiply everything by lambda. Okay? And so now if I add them, if lambda is small, everything is going to be positive, right? When I add them, what do I get? I get things like 2 plus 11 lambda, 4 plus 3 lambda, 8 minus 2 lambda, 7 plus lambda. How large can I take lambda and have everything positive?
4.
4. And once lambda hits 4, I have a problem. I could go the other way. I could take lambda to be negative. If I take lambda to be negative, well, let's see, lambda is negative 7. Once lambda is lower than negative 7, I'm in trouble. Over here, once lambda is less than negative 4/3, I'm in trouble. So I think I could take lambda all the way down to negative 4/3, and then I would be in trouble. So what we can do is we slowly either increase or decrease lambda until we kill off one of the coefficients. Okay, so I'm going to let you write that up rigorously. But that's the idea, is the non-zero elements here in X have elements here. These elements in gamma may or may not be 0. They may or may not be positive. It's only the elements of X that are non-zero. But all the elements of X are positive. So if lambda is sufficiently small, it doesn't matter if one of the coefficients is negative a trillion. Take lambda to be 1 over a trillion factorial, 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 factorial. Okay? Hugely small. Okay? You do something like that, and then this expression will still be positive. And then you can slowly either increase lambda to be small positive or small negative until you eventually knock off one of the coefficients of X. And what we've done is we now have a feasible solution with one fewer non-zero entry. Okay? So is everyone clear on what we've done? We started off with a feasible solution, and we showed if it's not basic, we could get a feasible solution with fewer non-zero entries. Okay. So let's isolate that. So we've shown, given feasible solution, if not basic, can find a new feasible solution with fewer non-zero entries. You have to be very careful how you write this. Is it exactly one fewer entry?
Maybe not.
Maybe not. It's possible. Maybe X was 1, 1, 2, and maybe lambda was 1, 1, 4. I mean, my gamma vector was 1, 1, 4. And then when I take lambda to be negative 1, I kill off 2 values of X at the same time. So all we know is that we kill off at least one more component. And so now I claim we're basically done. And the reason we're done is we've shown that if we have a feasible solution, and if it's not basic, we can find a new solution with fewer non-zero entries. So let X be a feasible solution with fewest non-zero entries. Remember, X has n entries. So the number of non-zero entries is either going to be 0, 1, 2, 3, all the way up to n. It's a finite number. And so we just look at all possible feasible solutions, and then just look at one of the feasible solutions with the fewest number of non-zero entries. If it wasn't basic, this gives us a way to find something with even fewer non-zero entries. That can't happen. Therefore, there has to be a basic feasible. So this is really nice. Feasible implies basic feasible. Essentially the same argument shows optimal implies basic optimal. Okay, any questions on what we've done so far? So this is a major step forward. Now we want to show that there's only finitely many basic feasible, right? So the problem is, there could be infinitely many basic feasible. Okay. So this is where we need some results from linear algebra. So, if I give you a basic feasible solution, what's the first thing that comes to your mind? So you hear the phrase basic feasible, what comes to your mind? One of two things should be coming to your mind. You should be fixated either on the word feasible or on the word basic, right? So, the key is the word basic. If I give you a basic feasible solution, the corresponding columns are linearly independent. So we have n columns. How many ways to choose k columns? So how many ways are there to choose k columns from n? And choose k, right? This is in some sense the definition of the choice function. That's a finite number, right? So all we have to do is show that for every set of k columns, there's at most one basic feasible solution, right? And if we can do that, we're done. So remember, A is n by n, and typically n is going to be much larger than n. If we don't have more variables than equations, it's an overdetermined system, right? So when we look at it, we look at like the sum, k goes from 1 to m of n choose k. And that's how many things we need to look at. And this is approximately, it's really given by just the last term. It's approximately n choose n. So this tells you how many finite things to check. If you want a really bad value, this is at most 2 to the n. Now when you think of n as something like 100,000, this is a large number. 2 to the 100,000 is greater than 10 to the 10,000. We are not going to be able to check 10 to the 10,000 things, but it's finite. Right. So our goal is to show that there's only finitely many basic feasible. And our plan of attack is to know, well, if I choose k columns, if I can show for every choice of k columns, there's at most one basic feasible solution, then there can only be finitely many basic feasible solutions. And in fact, the finite number is at most this sum, which is at most 2 to the n. Alright, so all we have to do now is show that for every choice of k columns, there's at most one basic feasible. Alright, so how do we do that? So, assume AL1, ALK are linearly independent, and X is basic feasible. Whereas always the non-zero elements of X are L1, L2, Lk. So let's let the matrix A prime be AL1, ALK. So what have I thrown away?
ALK plus 1, 2 from ALN.
I've thrown away the other columns of A.
Yes, the other columns.
Right? I've thrown away the columns of A that are hit by the zero parts of X, because they don't play any role. So this is a n by k matrix. K plus n. And we know, and this is where we need to use a few facts from linear algebra. The rank of this matrix is k. So matrix A prime of rank k, since we have k linearly independent columns. Okay? So we need to solve A prime x equals b. That's how we find a feasible solution. Subject to, and actually I'll call this x prime. Subject to x prime greater than equals 0. Well, I can forget about this constraint, right? Because if I can show there's only finitely many solutions without this constraint, then clearly I can't generate more solutions by including the constraint, right? So, to me this is math at its best, right? Throw in extra things, and if you still win, great. You know, be as lazy as possible. Let's try not to deal with that constraint because it's messy. If you could, looking at this equation, what would you love to do to solve it? What would you like to hit both sides of this equation with? You have a matrix equation. What would you want to multiply both sides by?
You're not saying inverse of
By the inverse, right? You want to multiply both sides by A prime inverse, right? Now, what's the problem?
So hard to get the inverse.
yeah.
With theoretical mathematicians today, it doesn't matter that it's so hard. That's not an issue for us because we're not actually doing the calculation. This is in theory. There is a problem, though, with trying to write down the inverse to A prime. Which matrices have inverses? Okay, the determinant has to be non-zero. And which kind of matrices have determinants? Square matrices. Typically, this is not going to be a square matrix. Right? So the problem is I need to multiply by an inverse, and the inverse doesn't exist. And okay, which try to generalize. If I gave you 3x equals b, you would say x equals 3 inverse b. We want to just generalize that, but sadly, we can't. So here's the great idea. What we're going to do is we're going to multiply both sides by the transpose of our matrix A prime. Oops, sorry, that should be. Is it okay to multiply both sides by the transpose of our matrix? Yeah, that's fine. Now, here's the question. What kind of matrix is A prime transpose A prime? Square. A prime is m by k. Its transpose is k by m. This is a k by k square matrix. So since it's a square matrix, what do you hope is true?
It's invertible.
You hope it's invertible, right? And we're in luck. It is going to be invertible because it's a k by k matrix and A prime has k linearly independent columns. This will be invertible. So if the inverse exists, we then get x prime is A transpose, I'm sorry, A prime transpose, A prime inverse, A prime transpose B. So if the inverse exists, this is what your basic feasible solution has to be. Now, this may not have all entries non-negative, right? That's fine. It just means then it doesn't count as a basic feasible solution. So if the matrix is invertible, this will be the only solution possible. So it's very important here. We haven't lost any solutions in doing this. So long as this matrix is invertible, we can uniquely solve for A prime, for X prime. So the question is, how do we prove that this matrix is invertible? It all comes down to that fact. Okay, are we all comfortable that it's all down to this one fact? Okay. Alright, so how can we prove that this matrix is invertible? So the question is, where have you seen stuff like this before? And so you might have actually seen it in calculating eigenvalues, or looking at projection matrices. So, eigenvalues, projection matrices. So we want to study A prime transpose A prime times X. What I'm going to do is I'm going to multiply by X transpose. And let's study this quantity. Why is this a good thing to study? Well, look, X transpose A prime transpose. When you take a transpose, you switch the order of things. This is the same as A prime X prime transpose times A prime X prime. What do you get when you have a vector transpose vector? This is its what? Well, this is going to be a number. It's the dot product, right? So V transpose V is basically the length squared. So this is just the length of A prime X prime squared. So if I have a square matrix, the only way it's not invertible is if it has a determinant of 0. Right? So the danger is determinant is 0. But that means it has an eigenvector with eigenvalue 0. It has eigenvector with eigenvalue 0. So, determinant of V equals 0 means BV equals 0V for some vector V. So what would it mean if this isn't invertible? Well, it means that there is some vector that is a eigenvector of A prime transpose A prime with eigenvalue 0. Okay? So if we take X to be that special vector, what would this expression be? If we take X to be that eigenvector, then what would this whole expression have to be?
Sorry, when you say determinant is 0, which one are you referring to?
It has to be A prime transpose A prime, because that's my only square matrix.
Okay, so you're talking about that.
Right. So, assume A prime transpose A prime has determinant 0. Let X be such that A prime transpose A prime of X equals 0. Right? Such an X has to exist. Right? That's the definition in some sense of having determinant 0. The span of the matrix, the rank is not full. Okay, well then that means if I keep using that vector, we'll let that be our X prime, we get X prime A transpose A prime transpose A prime X is just X prime transpose times the 0 vector, which is just 0. So that's told us that AX has length 0 for that special case. What's the only vector that has length 0?
0.
The 0 vector. So this means, AL1 XL1 plus ALK XLK is 0. But this violates the linear independence. Because we assume the columns were linearly independent. So the only way I can write this is if all of the x's are 0. And we've just shown that if this is not invertible, then I can find a choice of x such that A transpose AX is 0. That means this vector has length 0. That means this combination is 0. That means the columns are linearly dependent. So this is a contradiction. Contradicts the linearly independence. So our assumption is false. And that finishes the proof. So if it's been a while since you've done linear algebra, you should go through this argument slowly. I left it as just an exercise in the book for now. Flush it out and put in the details. But the main idea is we can associate a nice square matrix to our rectangular matrix. And the trick was to multiply by the transpose. And that got us a nice k by k square matrix. And it turns out that that matrix is invertible. And because that's invertible, then we could get a unique solution. And so, for every choice of k columns, there's at most one basic feasible solution. And since there's only finitely many ways to choose some columns, there can only be finitely many basic solutions. Okay, so we've proved 2 out of the 3 big theorems. The optimal theorem is done very similarly. So we've done a lot. We know that if there's a basic solution, a basic feasible solution, we know if there's a feasible solution, there's a basic feasible solution. We know if there's an optimal solution, there's a basic optimal solution. And we know that there are only finitely many basic feasible solutions. Now we want to find them. And so now we can finally get to the simplex method. So when you're trying to think of which results have changed the world the most, simplex method is up there. In terms of the actual implications to society from something like this, it's amazing. The ability to optimize difficult problems quickly. Small changes can lead to great changes in profit. In the supplemental textbook for this class, Mathematical Methods of Economics by Joel Franklin, he talks in chapter 1 of how he was visiting one of the big oil companies and he saw one of his friends from grad school or postdoc days who's no longer eating spam, but is actually in the big office. And he's seeing the big computer cluster the oil company has. He says, I know the oil companies have a lot of money, but they don't like to just throw it away. How long did it take them to recoup their investment? And being a good mathematician, his friend starts to stare into space and move his fingers through the air a little bit. And in a few seconds he says, about a week. That the expensive cost was recouped in about a week. Because very small changes led to more efficient allocation of oil to refineries, from refineries to cities. Being able to solve these scheduling problems is enormously useful. So the question is, how do we do this? And the simplex method has 2 steps. So phase 1, so we're always going to be given a canonical linear programming problem. Find a feasible, a basic, feasible solution, or prove none exists. So that's step 1. Does this seem a reasonable step 1 to trying to solve a linear programming problem? Check and see if there's a basic feasible solution. Right? The only difference between this and what I just said is the word find. Not just, does there exist a feasible solution, actually give it to me. Right? That's the difference. We want something a little bit constructive. Why? Because we're trying to solve things. You go back and you tell the airline, you tell the oil company, yes, there is a schedule that will maximize your profit. That'll be $500,000. The company will not be happy with you. They want to know what that schedule is. So it's not enough to just know there's a basic feasible solution. We want to find it. Phase 2 is the following. Given a basic feasible solution, find a basic optimal solution or prove none exists. And in fact, the way we'll prove none exists is we'll actually give a sequence with the cost heading towards minus infinity. Okay? So this is the simplex method. There's two phases. Phase 1 is we find a basic feasible solution or prove none exists. Phase 2 is given a basic feasible solution, we find a basic optimal solution or prove none exists. And we have to expect something like this because we know it's possible that there is no basic optimal solution. We know it's possible that there is no optimal solution to the linear programming problem. So we can't always expect a solution to come out. So, you're supposed to have read the notes, but imagine you haven't read the notes. What order do you think we would argue here? What should we do first? I have two procedures to construct for you. Which procedure should be constructed first? Phase 1 or phase 2?
Phase 2 is easier, I think.
The thing is that for phase 2 you would have to start with a basic physical.
So phase 2 requires phase 1, right? So what should we do first? Right? Phase 2 is basically saying, I want a basic feasible solution. I want it now. Right? This is what phase 2 is saying. So what should we do first? No, phase 2. So we do phase 2 first. So we assume phase 2. Assume we know how to do phase 2. We then show, knowing how we can do phase 2, we can do phase 1. And then, knowing how to do phase 1, we show how to do phase 2.
Why?
What seems to be the problem here? Does it seem like we're arguing in circles?
Yeah.
We assume we know how to do phase 2 and then we prove phase 1. And now that we know how to do phase 1, we prove phase 2. But in order to use phase 1, we had to know phase 2 first. So doesn't it seem like we're arguing in circles?
Yes.
It does.
Yeah.
Fortunately, we're not arguing in circles. We don't need to do when we assume phase 2, assume phase 2 for an easier problem. Then we'll do phase 1. And then, knowing phase 1, we'll then do phase 2 in general. So for instance, phase 2 says, given a basic feasible solution, find a basic optimal. So what we're really going to do is phase 2 prime, given a canonical linear programming problem with a basic feasible solution. Find a basic optimal or prove none exists. This is not the same as phase 2. This is phase 2 applied to a situation where we have a basic feasible solution. There are lots of times when basic feasible solutions are trivial. So again, if you want American Airlines, what is your goal?
Maximize profit.
Maximize profit. Now you're going to have all these different constraints on travel, right? You can't have one plane flying from one city to 2 different cities at the same time. When a plane lands, you can't use it immediately afterwards. There's time for the people to get out, the plane has to be checked. can you give me a schedule that will satisfy all the constraints you must have?
No flex.
No flex. Right? Do you have a feasible solution to running an airline? Yes, you're permanently grounded. Right? Imagine you own a movie theater. Can you give me a schedule to put the movies on screens so that everything will be satisfied? So you don't have two movies on the same screen at the same time, or one movie being used on two different screens at the same time. What schedule could you give me?
No.
No movies. Right? Let's say you want to ship oil from refineries to cities. Don't ship anything. Right? In many problems, it's actually easy to find a basic feasible solution. And so, to do phase 2, if we can input that basic feasible solution, then we don't need phase 1. The whole point of phase 1 is to find a basic feasible solution. Well, what if you already know one? If you already know one, then you don't need to use phase 1. So we're not arguing in circles. Again, it's only in the very special cases when we can just look at the problem and be divinely inspired. If I give you a harder problem, Major League Baseball, you have a 162 game season. You want to have each team play 162 games. They have to play a certain number of games with teams in their own division, interleague games, and everything like that. It's not trivial to write down a feasible solution for the baseball season. That's much harder, because you actually have to get in all 162 games. So I can't just immediately look down and say there is a solution, especially if you start putting on more and more constraints. But for things like American Airlines, movie theaters, those, yes, we can just quickly look and say that there's a solution. So the goal is to show that we can do a simple version of phase 2, what we'll call phase 2 prime. A very special canonical linear programming problem where the basic feasible solution is blatantly obvious. And so in the last few minutes, let me introduce you to the most blatantly obvious basic feasible solution linear programming problem you can ever find. Right? So the original is AX equals B, X greater than or equal to 0, and we want to minimize X transpose C. Okay? We're going to look at a new problem. I'm going to make this expanded matrix. I'm going to put an identity matrix down here. And I'm going to put in a new vector Z here. So X and Z have different sizes. So a little bit of abuse of notation. And now, in a moment, I'm going to have to tell you what we're going to minimize. But what we're doing here is before, we had AI1 x1 plus dot dot plus AIN xn equal bi. And now, we have AI1 x1 plus AIN xn plus zi equals bi. Okay. And so now, what are we going to try to minimize? We'll minimize Z1 plus, I think, what is it, Zn. So there's one subtle issue that I have glossed over. It's possible one of the b's is negative. Right? But I can, is there any harm in my assuming all the components of b are non-negative?
No.
No. I can always multiply through by a minus sign and change this equation, right?
Mm-hmm.
So, without loss of generality, each bi is greater than equal to 0. canonical form wasn't quite canonical enough. Let's assume each component is non-negative. Okay, so each component is non-negative. Can you give me a solution to this with the x's and the z's, where all the x's and z's are non-negative, and it solves this equation? So can you see a solution?
Z is 0.
I'm sorry?
Z is...
Not z is 0.
You just say Z is non-negative.
Right, but if z is 0, then we're back to trying to solve the original problem, which is how.
Right.
I claim there's a really easy choice of the x's and the z's that will solve this equation. What's a good choice for zi? And what's a good choice for the x's?
0.
Right? Solution. X equals 0. Z equals b. Will that solve the problem? Yes! We have found a solution. Right? So again, in general, if I give you a linear programming problem, I can't expect you to be able to look at it and solve. If I ask you to come up with a schedule for Major League Baseball, I don't expect you to just whip it out. But for this one, yes we can. Right? Essentially, we're saying forget about the x's. Okay? What we want to do now is, and we'll talk more about this next time, we know the existence of a feasible solution. Phase 2, or phase 2 prime says, given a feasible solution, given a basic feasible solution, we can find a basic optimal or prove none exists. So clearly our solution here is going to be optimal because the corresponding columns is just the identity matrix. So this is going to give us, I'm sorry, a basic solution. Basic feasible. Now, what's the smallest the cost could be? So what's the smallest the cost could be?
0.
0. If the cost is 0, what can you say about the z's? The only way the cost can be 0 is if all the z's are?
0.
If all the z's are 0, then we're just solving the original equation. A basic optimal solution to this problem is a feasible solution to the original. So, basic optimal here is basic feasible in the original. So we'll go over this again next time because this is the key idea in the method. It's what makes the whole thing work. It's absolutely amazing. It's one of the greatest ideas I've seen. Right? Phase 2 requires a basic feasible solution as input. We take our problem and we tweak it, and we get a new problem where we can just see the basic feasible solution. Then we apply phase 2, which generates an optimal solution, a basic optimal solution that tells us none exists. If the basic optimal solution has a cost of 0, the only way that could happen is if all the z's are 0, in which case we have a basic feasible solution to the original problem. If the cost is not 0, then there was no basic feasible solution to the original problem. Why? If there's a basic feasible solution to the original problem, then the smallest cost just has all the z's equal to 0. So if there's a basic feasible solution to the original problem, then the optimal cost is 0. So we'll talk about this again, but what this tells us is we're making real progress. We basically now have phase 1 of the simplex done. If we could only do this phase 2, given a basic feasible, somehow move to a basic optimal, we'll be done. And that's what we'll look at next time. Okay.